Welcome to the course Digital Transformation and Technological Innovation. So, we are into our fourth module, that is Tech Advancement and Internet Basics. So, let us continue our discussion from where we left in the previous session. Right. So, we were talking about the various aspects of internet and networking. Now, to continue with that, our next point to understand is network routers and the role of network routers there. Now, computing devices, so what are network routers? So, these are actually computing devices that connect networks and facilitate the exchange of data between them, right. So, router to router, so that connection is there and the exchange of data is there. So, network routers in a way are computing devices themselves, and they themselves are connected to internet. So, these routers have their own IP addresses and they are connected to the internet. So, these routers are computing devices that connect networks and facilitate the exchange of data. So, the main role of router is to facilitate the exchange of data between them, between routers and between computers eventually, right. So, routers have their own IP addresses and connected to the internet. Now, routers communicate with each other and with other computational nodes. How? Via IP, internet protocol. So, they have the IP address, and then what is their role in this process? Process of exchanging the data, allowing facilitating the exchange of data between computers. Their role is to do the relay walk for packets. So, packets that we talked about, different protocols, right, and TCP and IP, and the packets, the relay walk for those packets from happens from router to router, right. So, these routers communicate with each other and also with other computational nodes. So, one of them would be client and then server would be there, right. So, this whole communication with each other and other computational nodes is done via IP, and routers do the relay walk for the packets. Now, these packets that we just talked about, they might traverse several networks to reach the their destination, because the server machine might be sitting in US and the client might be here in India, and therefore, the whole network that connects a client device through routers, through home business router, and then other network routers, the internet core routers, and back to the same the back to the US side of network. So, therefore, packets, when we access a website which is hosted in US, and essentially the packets traverse several networks across the continents, right, to reach their destinations, right. So, the vast majority of computers on the internet connect to a router, because essentially that is how the internet connection is established between a client and the server. There would be connections from computers to routers, and those routers to other routers, and eventually the connection to even the server machines, right. So, the overall we can say that vast majority of computers on the internet, they connect to a router, right. Now, there are some other technology which might allow the bypassing of from the router, but most of the network is connected through a router. So, therefore, we can safely say that vast majority of computers on the internet connect to a router. Now, a router is almost always connected to two or more routers, right, linking up the networks, and that is how it makes up the internet, right. Now, theoretically there might be just a router might only be connected to one or more routers also, but more often than not, almost always in practice, just like I said, that vast majority of computers will be connected to a router, but as I said, there can be other technology to bypass that. Similarly, in practice, a router will almost always be connected to two or more other routers, and that is how the network gets created. The packets could be relayed, and the communication can happen through protocols like TCP and IP, right. So, here we have a diagram which depicts the whole thing, and you can see these devices which are represented with capital R, these are routers, right. And here is the web content on the web server, and you have web content on the user device. So when you are opening a browser, either on your desktop or smartphone or tablet, and you are typing in the URL, and the TCP will walk here, and will do the assembly and reassembly, the ordering thing, and all those aspects we talked about in the previous session. Then once the packets are there, and this particular diagram is showing when the content is being sent from the server side to the client side, so the page is to be downloaded. So this page would be big enough, and this page is to be divided into this page would be too big for the network, and it will be divided into packets, and these packets will go through the routers. So you can see the packet 1 has taken this route, and the packet 2 and 3 have taken this one, and they go this way, and then they go this way, right. So there can be multiple paths to reach the destination. For example, from here the packets might have taken this path also, but this was not taken, and packet 1 goes from here to here, and then from here to here. So essentially for the same page which was divided into different packets, different chunks, and these different different packets might take their own path to reach the destination, and here the TCP again comes back, which reassembles these packets, and the page is displayed here, right. So here the page was divided into packets, and here these packets are put together or assembled to create the page. So TCP is controlling that data part, assembly, reassembly, ordering part, and the IP is essentially managing how the packets, how the smaller chunks of the packets how they travel through different routers and travel through the internet. So and they might take their own network path. So this is how it happens. Same pretty much similar thing happens in other protocols also. So the next protocol that we are going to discuss is user datagram protocol, UDP. So while TCP has its own use cases, like we talked about SMTP, HTTP and FTP, those kind of services are delivered via TCP. Similarly, there are lots of services which require much faster speed, and they can give away the reliability, the absolute reliability. Essentially, when we say give away the reliability is there. It might not be absolute, might not be 100%. So, but in case of email, in case of looking at a particular page, or getting a computer file from the remote system, you would like that particular data to be perfect. So absolute reliability you want in those cases. So TCP is more suitable for those applications, right? But there are applications where you can compromise with the absolute reliability. If small tiny part of data is missing, still you can do with that, still you can walk around that, right. So user datagram protocol is more suitable when speed is desired. So it is a lightweight connectionless transport layer protocol. So just like TCP, this is also another example of a transport layer protocol. This is lightweight and connectionless. TCP was connection oriented, right, and this is connectionless, so designed for speed and efficiency, right. So when faster sending and receiving of packets needs to be done in an application, then maybe UDP is more suitable in comparison to TCP. So what UDP does, it simply blasts blasts data packets or datagrams directly to the destination, and it does not check whether the receiver is ready, online, or even getting the data or not. It starts sending the data packet. So that reduces the time and the it reduces the latency, and it speeds up the whole process of sending the data packets, right. So that's why the applications where the speed is prioritized, those applications might prefer UDP based implementations, right. So UDP skips all overhead, right, like we said, It's not checking whether the receiver is ready online or even getting the data. So there is no handshake. And the handshake thing that we talked about in the TCP case, so that handshake is not there, and it doesn't check for that and starts sending the data packets. That makes it fast. But obviously the applications which are okay with a bit of loss of data, for those applications UDP might be suitable. So it skips all overhead, and thereby it achieves virtually zero latency. So there are applications which actually prefer this. Some applications, right, distributed computing applications, they would prefer virtual zero latency or delay, and this is, as I said, in contrast to TCP, which carefully manages connections and fixes error, because their complete masses, retrieval of complete mass is very important for the applications which use TCP, and TCP therefore does that part, carefully managing the connections and fixing errors and all that. So that we have discussed, UDP is works in contrast to TCP and favors the speed and prefers zero latency. It's connectionless. Another characteristic of UDP is that it's connectionless. So UDP does not perform a handshake mechanism like TCP, right. So that reduces the overhead. This overhead that gets reduced because there is a no handshake there, right. So it transmits data immediately without establishing a formal connection first. So formal connection is not really established, and the data starts transmitting data immediately, and that makes it fast, right. No delivery guarantees, right, because as I said, UDP is more for the speed and doesn't really target the absolute reliability. So therefore there are no delivery guarantees. So UDP will not notify the sender if the packet gets corrupted, dropped, or completely lost in transit. So if there is a loss of packet, if there is a corruption of the packet, right, it get dropped, then there is no notification mechanism, there is no handshaking. So therefore UDP is more suitable in applications where by the time this handshaking and notification, if it was implemented, if it would have been done, it will become meaningless, right, because the time has gone by, right. So very real time applications which require very real time fast communication, and anything that comes late, it becomes meaningless. In those situations UDP is more suitable, and its mechanism or characteristics of not notifying the sender, it fits in those kind of scenarios. No order delivery. So as we discussed that at the IP level, packets anyway can take different routes across the internet, and UDP will not be looking to ensure the order delivery, right, and therefore the applications for which UDP will be used will also have the will also be having that kind of environment where even if the packets come out of order, it doesn't affect the output, it doesn't affect the processing that is happening for those applications. So no order delivery is another characteristics of UDP, and UDP does not rearrange datagrams that arrive out of order. So that means the application should not be needing this mechanism where things are to be rearranged and ordered and all that. So and the same thing is so applications which are actually going for UDP implementation, obviously they must be okay with that, with this situation that UDP will not be rearranging datagrams in case they are out of order, right. So UDP passes such datagrams straight to the application layer, right. Directly these datagrams are boosted towards sent to the application layer, and application handles this data there. Another characteristics of UDP is that there is no flow or congestion control, right. So UDP sends data at whatever speed the application demands. So it's a very real time fast application. Then the speed at which data is required might be slightly demanding. So UDP will match that speed, right. So UDP sends data in whatever speed the application demands, and for this whole thing to be able to do that, it removes lots of overhead. For example, it does not check whether the network is completely jammed or not. So there is no extra checking and ensuring that errors are not there like the TCP. So it does not check whether the network is completely jammed or not. It will not check whether the receiving device can process fast enough or not. So those checks are not done. So those overheads are not there, and that makes UDP quite fast, and therefore it is able to send data at the speed desired by the application. So there is a no flow or congestion control that is actually managed by UDP. So then, after discussing all this, and you have already you must have already understood that when the UDP can be used. So UDP is actually has become sort of absolute standard for applications that prioritize real time instantaneous delivery over flawless data perfection. So the applications which are not looking for flawless data perfection, and they are rather prioritizing real time instantaneous delivery. So for those application, UDP is absolute standard, and UDP is the preferred approach. And in many of these settings, what has been observed that waiting for the lost packet to be resent is useless, because the moment has already passed. So the time when that lost packet could have been used in the output, could have been used in the processing, that time has gone, right. So there is no point in waiting for the lost packet for those applications, because essentially we are saying the applications are real time and instantaneous delivery kind of applications. So they are doing real time instantaneous processing, and for that waiting is not really needed. So if we look at the examples of applications where UDP could be really useful, so those applications would be live video streaming, right. So in a video that is being streamed out, even if some tiny portions of the pixels which are somewhere in the bottom side or the corner side, even if they are not received, still you can make out what is happening in that video. So therefore that absolute or the flawless data perfection is not really needed for the video and image based applications, because few pixels in the corners here and there will not really disturb will not disturb the end user experience too much, right. Rather the end user might be having a low bandwidth connection, so they already know why this is happening, and they might be okay with what this kind of small loss that might be there. But faster delivery is important, because people would be looking for real time experience of what is happening in a particular sports or in a particular event. So they do not want to miss out on the real time action, and therefore UDP is faster and supports those kind of applications. Similarly, VoIP, voice over internet protocol. So nowadays all of us, we prefer making WhatsApp call. It also reduces our, in case we have to make an international call, it reduces our cost, and similarly there are many other apps. So which are lots of meeting apps that we have, like Zoom and Microsoft Teams and other. So all those actually rely on VoIP, voice over internet protocol. So they are also the underlying transport mechanism is driven by UDP, right. So because the meeting, again same thing, images, videos, few pixels here and there might not really disturb the end user experience, but rather real time delivery is much more important. What a person is saying in the meeting, that should come real time, because the other person might have to respond back, right. Similarly, online multiplayer gaming, lots of players connected via internet playing the same game, and they having their own characters in the game. So they are also for real time action, right. UDP would be preferred. DNS lookups also pretty much similar scenario. You are just looking to find the IP address for a particular domain name, and there also you might prefer the speed because you want to you want your device to quickly load the page. For that you favor the speed. So, UDP based implementation for DNS lookup might be more preferable, right. So, these are some of the scenarios where UDP can be used. Now, we will talk about the voice over internet protocol, because this is something that has become part of day to day life. So, what this technology is about? So, this is a technology that allows voice calls, video calls, and sending multimedia messages over the internet, right. So, what it does, it will rapidly convert the speaker's natural voice, acoustic voice, into digital data packets, because in the internet world it is the digital data packet which will be transmitted over the internet. So, therefore, a conversion will take place. So, VoIP one of the steps would be convert the acoustic voice, right, coming from the natural environment, natural setting, into a digital data for the digital environment, that is internet, and for the transmission of that data. Now, VoIP, as we already know, is heavily used today, and it is in a way effectively replacing the traditional analog telephony. So, you would already notice that many people preferring to make a WhatsApp call, because there are messages also you can confirm whether from your past messages whether you are calling the same person. There might be photograph also. So, there are less chances for calling the wrong person. There are other reasons that add up, right, but essentially VoIP technology, for example WhatsApp call and other calls, they are effectively replacing the traditional analog telephony. So, traditional call via mobile phone or a smartphone, that usage is reducing day by day. Now, what are the steps in the VoIP? So, first is conversion. So, first analog to digital converter ADC is used to translate the voice waves into binary digital data. That is first step, the conversion takes place, that is done by the protocol VoIP technology. And then the compression, because you would be transmitting the data over the network. So, we would like to compress this so that it takes lesser time to transmit the data. So, a specialized software called codecs which are known to compress the audio data. So, they will compress the digital audio file, and therefore, less data transmission would be required, and therefore, faster delivery will happen. So, that is done. Compression is the next step. Then, because the compression has happened, so little bandwidth will be needed. That means a VoIP call, if the compression step is there, compression happens, then it might work even on a low bandwidth connection, right. So, sufficient clarity can be there even with the low bandwidth connection. Then the next step is encapsulation. So, the compressed audio data is then chopped up into fragments and placed inside the UDP transport datagrams. So, it is the UDP that comes into the picture after the chopping of the audio data, and the UDP then does the faster delivery of this data. The transmission takes place. So, packets, they will actually travel across the internet, and they will be bouncing from router to router and using the destination IP address of the recipient. So, this transmission takes place, and the data is transmitted in that manner. Then once the data is received at the recipient side, so recipient device will catch the packet, and it will decompress them, because in the previous step, as you notice that here before before the chopping, we had compressed the data using codecs, right. Now, when the data is received here at the recipient device, then we need to decompress it, right, because we need to then do the conversion again. So, decompress them and then rearranges them. So, rearrangement will be done, decompressing will be done, and then it routes them through a digital to analog converter, right. So, if you DAC, so if you recall, the first step was analog to digital converter. So, a speaker was saying something, and that acoustic voice, right, that was converted into a digital format because it was to be transmitted through the network. So, analog to digital converter ADC happened. Now, later when the digital audio file or digital audio data is received, then you have to convert digital back to analog, so that the listener can understand what was said by the speaker. So, digital to analog converter will play its role, and it will do the conversion from digital to analog and play out the speaker of this device, smartphone or any other device, as clear sound. So, these are some of the steps that are actually followed in this process. So, with this we have completed some important protocols. So, what we will do a quick recap of what we discussed in this session. So, we started with the role of network routers and how they connect the network and actually make up the internet. And these routers, we talked about that they have their own IP addresses, and therefore, the communications between the routers and other computational nodes happens via IP, internet protocol, and the main role for the router is actually the relay walk for the packets, right. And when we talked about when we are accessing a website that is hosted by server in US, then essentially the packets for that communication to happen, these packets traverse through several networks across continent to reach their destination, right. And then we talked about how the computers are more likely to be connected to a router. There are other means also, but more likely to be connected to a router. Similarly, routers are also more likely to be connected to 2 or more routers, right, and that whole thing makes up the internet, makes up the communication possible, makes up the relay of packets possible. Then we went through this diagram, and we understood how the content is broken into packets, and they can take different path through different routers, they can take different network path, and they will reach the destination where TCP will do the reassembly and all that part, right. So, this gives us a clear idea about what happens to those packets through the network, where the IP comes in, where the TCP comes in. So, that part becomes much clearer. Then we talked about the UDP and how UDP works in contrast to TCP, and it prefers virtual zero latency, it prefers speed over absolute reliability, and therefore, it is more suitable for applications which are looking for real time data and instantaneous processing, right. So, we looked at different actions, how UDP is able to manage the speed, because it does not do handshake, it drops lots of overhead, it does not notify and it does not it does not do the rearranging and all that, it directly gives the data to the application, right. So, therefore, it is able to manage the speed that is needed, and it does not do the checks for traffic, network traffic, and the speed at which the receiving device is processing. So, it does not do lots of checks in terms of flow or congestion, right. So, therefore, use cases, as I said, we have discussed real time instantaneous, right. So, and these applications where UDP is used typically if a packet is lost, then it will be meaningless to get it back, because that moment has passed and that packet is no longer useful, because you are in a real time application case. Some of the use cases for UDP are live video streaming, VoIP, online multiplayer gaming, DNS lookups. Then we talked about the voice over internet protocol VoIP, which has become important applications, and there we talked about that first step is that analog to digital converter will convert the acoustic voice to digital voice, which will be compressed first, because it has to go through the network. So, we would like to have lesser data that goes through the network, we would like to compress it so that it reaches faster, and then chopping happens, it is sent via UDP, and then transmission happens across the network, and then reassembly. We need to decompress the data, get it back to the analog format from digital to analog, and then play out, right. So, this was about some of these important protocols in the networking context, internet context. We will continue our discussion in the next session. Thank you.